Okay, today's lab is the so tricky named putting the force before the cart. Hi, Leslie.
Hey.
The point of today's lab is to actually check to see if what I've been telling you about Newton's second law is true. So Newton's second law is our goal to understand. Newton's second law is... Who can tell me what Newton's second law is? I'll write it right here. Who can tell me what Newton's second law is? It's the one we talked about with the equation. In case you're like, I'm not sure if that's the second one. Let's go to the lecture material then. Whoops, wrong lecture. Okay, we've talked about Newton's second law a little, but we didn't get all that far into it. Newton's first law of motion is the one about inertia. Newton's first law of motion would explain why if I put this on the paper and slowly pull the paper, it moves with the paper. But notice I do it with a yo-yo and paper and not my fine glassware. If I take this and I yank it quickly, it stays there and doesn't come with the paper. Why? Because it had inertia, it had a resistance to change in motion. And so when I yanked it quickly, then the force of friction was not enough force to get it moving with the paper, and it hardly moved. Whereas if I go slowly, it doesn't take much force to get it moving because you don't have a large acceleration and it moves. That's what that's all about. But it illustrates the inertia, that the natural tendency is to stay stationary and you have to apply a force to make something move. We're not going to answer these questions. So, well, actually, this one here is really an important question, and it's not specific to that. This one here is boring. This one here is more fun. This is a really good demonstration of inertia. If I take this and I swing it around in a circle, okay, let's go this way. That way no one will get hurt, right? If I swing around the circle, and if I let go at the point when the bob, that is the rubber stopper, is straight below my hand, what direction is the bob going to go? Okay, I have vertical.
It's going to go to the point to where it breaks.
Well, it's not going to.
Oh, no, sorry. When it lets go, sorry, it'll like go not too far from the direction where you let it go.
Okay, it says not too far from the direction it was going when I let it go. This being a science class, science, you always test things. And so I'm going to try to let go right when it's at the bottom of its swing. Now, I'm never perfect on this. Yes, I was not very perfect. Because it went down and hit the ground. It should have just gone horizontally. But you have to let it go at just the right moment. And so I'll do it again just because it shouldn't have been that hard. Hello, Alexander.
Almost on time.
Yeah. We didn't get together and set up, so I did it.
Oh, yeah, let's do that.
So there I let go a little too late, so it went up. But the key is, at the bottom, what direction was it traveling? It was traveling that direction. So if I let go at the instant it's at the bottom, it will start off traveling that direction, then gravity will make it fall from there. So that's why it didn't stay in a straight path that arced downward, because gravity acted on it. A lot of people make very simple misunderstandings on this. A lot of people say, well, it's pulling out. I know if I swing it around a circle that it's pulling out on me. And so they say, well, since it's pulling out, if I let go of it right here, it must go the direction it was pulling, so they think it would go that way. That's not right. Why is it not right? Because inertia says that it was going this way and it just wants to keep going that way. And so then you have other people that say, well, I know it's not going to go straight out, but it's got some outward thing. And so they come up with something like this, which is also wrong. It's going to do this. Now, say it's going to do this. That demonstration is all I can really do to demonstrate that that's what it's going to do. Why do I have to pull in if it would go in a straight line if I were to let go? You ever thought about that? Because certainly, notice he walked out one door came in.
I forgot the key.
Nice. Can you bring out the washers, by the way?
Yeah, where are they?
Second aisle up on your left against the wall in the cupboard. I know that was really clear. He'll just try a lot of drawers and find it. Cupboards. This is something that Newton himself looked at. Remember, Newton had his really great year because there was the Black Plague. And he realized that gravity acts at a distance. That is that you have an apple in a tree, and once it breaks away from the tree, nothing's acting on it, and yet it's accelerating downward. Accelerating downward, according to his second law that he had just come up with, meant it had to have a force on it. So it said there was a force acting at a distance, which was actually earth-shattering ideas. Up to that point, they thought, there's no way I can put a force on you if I don't touch you. I can't just go, oh, and all of a sudden Gabby's like, oh man, he just pushed on me, right? Because the force is anything that pushes or pulls. And then Newton says, no, actually, we have forces at distances. So if I jump off the ground and I'm not touching the ground, there's still a gravitational force from the earth pulling me down. See, I told you to find them.
Yeah, we have different definitions of what an undeniable is.
Yeah. But he found them. And so Newton said, well, if there's a force of gravity acting on an apple in the air, then there should be a force of gravity acting on the moon. The earth should be attracting the moon. Is the moon falling to the earth? We physicists shake our heads this way. And then you say, you physicists are crazy, right? Because you all shook your head this way. The moon, if there was no gravity, what would the moon do? It'd fly away. It'd be just like this picture. Here's the earth. There's the moon. And the moon would just fly away. It'd get farther and farther away, and we say, bye, 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 moon. But it doesn't. There's the force of gravity acting on it that's making it accelerate toward the earth. That's why we physicists say, then it's falling toward the earth if it's accelerating toward the earth. But because it has its velocity that's taking it, change color, its velocity that's taking it this way, as it falls toward the earth, it falls away from that line and keeps going around a circle. Now, trivial facts that you don't have to know. The gravity of the moon acts on the earth and causes the water closer to the moon to be pulled more toward the moon than the rest of the earth. And so high tides, it also, on the other side, it causes water on the other side to not be pulled as much. And so you have high tides on the sides of the earth that are facing the moon and away from the moon. That's a first approximation. Now for the second. The earth is spinning, the moon is orbiting. Because of the earth's spin, we have what we call tidal friction. The water moves with the earth, and because we're spinning a lot faster than the moon is, it takes 23 hours, 56 minutes or so for the earth to do one rotation. It takes the moon around 28 days to do one orbit around the earth. So the earth is moving faster, and what happens because the earth is moving faster is the high tides actually are shifted forward and not straight at and away from the moon. Why is that important? I mean, sure, I suppose if you're a surfer and you really want to know when high tide and low tide are, that'd be important to you. But the net result is that the Earth's high tide leads the moon and causes the Earth's gravitational pull on the moon to be a little bit forward. So the Earth is pulling the moon forward just a little bit. And if you pull it forward, it goes faster. And so the moon is slowly gaining energy, as we say. It's going faster. And because it's going faster, it's slowly moving away from the Earth. So the moon moves, I think it's about 1/4 of an inch a year that the moon moves away from the Earth. And so in millions of years, the moon will be way out there. Of course, I believe Christ is coming along before millions of years. But it's interesting that the moon is slowly moving away from us. So in your lifetime, the moon has moved about 1 foot farther away from foot. Yeah, and it's not that much. But in my lifetime, let's see, this requires more advanced math. 51 divided by 4. It's moved that many inches away from the Earth in my lifetime, which is, significant to me, not to the moon. Okay, getting back to the topic. So we've talked about inertia. Oh, another thing that's kind of just fun physics tricks. Have you ever seen a demonstration where a person lies down on a bed of nails? No? Well, you're not going to see it from me either. You're not going to see it from me because you can do it wrong. Like you have to lie down in a nice, smooth fashion. I tend to be jerky. If you sit down first, well, then you've got nails in your rump, and that's no fun, right? So I don't do that. People who do that demonstration will often do something like put a brick on their chest. That's putting more weight. And then they'll have somebody with a sledgehammer hit the brick with the sledgehammer. And the brick shatters and they're still fine. You guys ever heard of that?
I think I've seen a little clip on it.
The reasons they do these things, first of all, lying on a bed of nails is in theory safe because each nail has a certain area and pressure is force divided by area. And if you have a bunch of nails, you have accumulated a pretty big area. And so each nail only has to support a small amount of weight on the nail because you distribute your weight over all of these nails. And then the pressure for each nail is pretty small because it's a small amount of weight per nail. And the pressure is less than the strength necessary to puncture skin. And so you're fine.
How do you get on?
That's again why I don't do it, because I would do something stupid and end up puncturing my butt. Right? When you do it good, what you have is a platform on either side with the nails about equal with the platform. So you sit on the platform, then you lay back on the nails, and then you sit back up on the platform. That's the way you do it right. Right? Then you aren't going to puncture your butt. Put the brick on your chest. You're adding weight that once again is distributed over all of those nails, so it's not a significant increase in pressure. No big deal. Get hit with a sledgehammer. Your body has a fair amount of inertia, and so does that brick. So when the sledgehammer hits the brick crumbles before your body really moves. And so basically all of the energy of the sledgehammer is absorbed by the brick. If somebody hits softer and doesn't break the brick, it's actually going to cause more pain to the person than if they hit hard and shatter the brick. Fun physics tricks. Most fun of all, one of my professors when I was in graduate school would do the demonstration. He would come out wearing a button-down shirt, unbutton the shirt to reveal a t-shirt, always keeping his chest to the class. He would come, sit down, lay down, do the whole thing, get up and say, "See, no problem at all," and then turn around and go to the board, and they would see on his shirt on the back a whole bunch of red points, which he had his office worker use a red pen to do that. But the joke was then the students think that he's lying about it being no problem and that he really hurt himself. That's the kind of sense of humor we have. You just have to know all of this stuff. I know it's really relevant to you. Let's move forward. How many people have heard of the flat earth arguments? You see them all the time on Facebook, right? And they make some claims that make me just shake my head. And one of them is something like this. If you're in an airplane and you flip a coin, why does the coin just go up and come back down? You're traveling really fast with respect to the Earth. Why does it just go up and down? You ever thought about that? Because these flat earthers they come to exactly the wrong conclusions.
It comes down because you're not actually moving. It's just screens on the window to make you think you're actually flying around the earth.
He likes to mess with you, okay? Alex was not telling the truth. God, Alex. Yes. It's all an elaborate stage set to make you think you're moving. No. The coin is moving, you're moving, you have inertia. You're going to stay moving the same way, right? Unless something happens. You hit turbulence and it pushes you around. Well, that coin's going to do the same thing. You flick it, okay, you gave it a violent motion, as Aristotle would have said. You made it start going up. It still had the horizontal velocity, and it just stayed with the same horizontal velocity as it went up and down. So since it was going horizontally the same speed you were, it appeared that it just went up and down because you were both moving horizontally at the same speed. Or the next slide here, I think, shows a bird in a tree. And flat earthers say this is the ultimate proof, or one of the many ultimate proofs for them, that the earth is not rotating, that it's not a rotating ball. Because the flat earthers say that bird should be traveling at thousands of miles per hour because of how fast the surface of the earth is moving. And when it leaves that tree, it should just go whoop and disappear because it's going so fast. You guys ever seen them argue that? Because they do. And I'm like, what sense would that make? I mean, the earth is rotating, and what do we have all around the surface of the earth? All this stuff. Air. And what's that air doing? It's rotating with the earth because you have the earth's surface is moving, and then the air that would come in contact with the earth's surface would be pulled with the earth, just like I showed you about the tidal friction making water pull forward. And so the earth is pulled by the surface of the earth, and then the interaction between air molecules makes them all speed up more and more until we've reached an equilibrium where all of the air is orbiting the earth at the same rate that the earth is rotating at the surface. If you go up higher, you have other things going on because of things like the Coriolis effect that make it so you have jet streams, which is why it takes less time to fly. Let's see, I got to get this straight. I think it took less time to fly from Asia to here than it does to fly from here to Asia, well, from California to Japan, to be specific on my most recent flight, because of the higher airs not going the same speed as the surface of the earth. So just want to point out a few things where the flat earthers have arguments that make no sense. And you can argue with them all day long. They're wrong, but they are so sure of themselves that they can't be proven otherwise. So see, here's the speed the surface of the earth is moving, 30 kilometers per second. It can, of course, drop down and catch the worm because it's moving at 30 kilometers per second. The earthworm is moving at 30 kilometers per second. They just stay with that horizontal motion and no problems. Okay, now to Newton's second law, what we're going to talk about. Newton's second law is talking about the relationship between force and acceleration, and we write it like this. The acceleration is equal to the net force divided by the mass, or if I multiply both sides of this equation by mass, then I have the net force is equal to mass times acceleration. Now, something that I'm a real stickler for that our textbook author is not is the word net, or the math symbol sigma, which stands for sum. It has to be the sum of the forces. It's not an individual force is mass times acceleration. If it was, then I would constantly be accelerating downward because of gravity. It's the net. It's adding them all up. And so this is the equation that we are going to be testing. We're going to be testing the relationship between three variables: acceleration, mass, and force. So at the end of today's lab, ideally, you'll be convinced, yes, I did experiments, and the experiment showed that this is the way it works. So what are those experiments going to be? Let's go back to the lab page. That's not lab. That's lab. So we're testing sum of the forces equals mass times acceleration. It's a vector equation, but we're just testing it as a scalar. That's we're going to have only motion in one direction. The things you need, by the way, should be on the front four tables, 2 people per table. The dynamics cart, let's see, I'm going to have, it doesn't look like I put one in front of you. Rachel, is there a cart in front of you? No. Okay, if you just open the cupboard to the side, there's carts in the cupboard. I guess I forgot carts for the back 2 tables. I have them for the front 2. Okay, I forgot cart only for your table. There should be cart. Okay, go ahead and pick yours up over here. You picked it up a second ago. There should be a cart like that. That's your dynamics cart. And then you have a mass block. You should have a little weight that is sitting there, a bar that's about this long in black. And that mass block is 500 grams in mass. Then you have string right here. You have to cut the string. And only the burliest of burly people can cut the string, because this is how you cut the string. It's the weakest string ever. So somebody apparently took exception with me calling it string and wrote on one of my spools, "I'm twine." I don't care. Pulley. There's a pulley at each station. At least I believe I got one out. A wood block or end stop. There should be we're actually not going to use the end stops. You're going to catch it with your hand. A paper clip. Paper clips are in my office. 4 hex nuts. Instead of hex nuts, we're going to be using washers, the things that I had Alex get. And you will just replace, when it says a hex nut, just replace hex nut with 2 washers. So if it says 2 hex nuts, you're going to put on 4 washers. And if it says 4 hex nuts, then you're going to put on 8 washers. Understand? And then the computer, there's a computer in front of all of you. Motion graphing software, we'll have to get things set up in a minute. And the motion sensor and interface, we're going to use the pulleys as our motion sensors. So you're going to set up a system. We're not using this, we're actually using string with the paper clip that we put washers on. And we're measuring with the pulley. And we're not going to have a block to stop. You're just going to catch with your hand. So the first thing you're going to have to do is set up all of your equipment. There's specific instructions here, so you can go ahead and follow those instructions. Get to what you're going to do. You're going to start here. Notice part A is vary the force. You start with 2 hex nuts, and we're just going to change that to 4 washers attached to the paper clip. So hang it on the paper clip. Pull the cart back so that the paper clip is hanging about 2 inches below the height of your track. And then you start the experiment and you let her rip. And it's going to go down the track, and you're going to first sketch a graph in the space to the right of the position as a function of time, I believe. I actually didn't pay attention to what the units were on here. And show the smooth. Yeah, so you're going to have position on this axis and time on this axis. Our software is going to make position as a function of time, speed as a function of time, and acceleration as a function of time. But you're only going to graph here the position as a function of time. So you'll put your graph inside that box. Also, scale it to fill the screen, and do a screen capture of this. For this one here, you'll just have one set of pictures that each of you will submit for yourselves. So if you're working, let's say Ivy and Gabby are working together, you'll just save one set of the pictures, and then each of them will upload that set for their submission. So you're going to upload this graph, and then you answer questions. So there's an answer here and an answer here. And then you change it. Instead of add the 2 remaining hex nuts, I'm going to say add 4 washers for a total of 8. And so that's going to double the force. According to Newton's second law, what should that do to the acceleration? If I double the force, what should happen to the acceleration? Acceleration is net force over mass. Well, I'm not going to tell you the answer right now because you are going to test and see. So you're going to do it and then answer here, how's the acceleration caused by the doubled force compare with the original acceleration? So you can look at your graph of acceleration and see what the acceleration was initially. In fact, right here, just put acceleration equals and write down the value that you get from your graph. And then on this one here, write acceleration equals and then write your comparison. By the way, what are the units of acceleration? Right. So make sure you put meters over second squared for the units. Right? Because if you just put a number, that's kind of meaningless. That's like saying, I live 3/4 away. Is it 3/4 of an hour drive? Is it 3/4 of a mile? Yes, it is. Is it, you don't know without having the unit there. Okay, then you have to measure the mass of your cart. Measuring the mass of the cart will accomplish with the triple beam balances. So there's a triple beam balance right behind you, ladies. There's a triple beam balance here, another one there. These here are not hard to use, but if you've never used it, you could be confused. So the first thing you do is you put all of the sliders to the left in their 0 positions. Now the big ones, they actually have a notch, so you can make sure they're in the right place. You can actually, some of them, this one you can't, but some of them you can lift and move them farther left than the notch. You want to make sure they're in the notch. The little slider just goes as far left as it can. And then you let it sit here and you say, is this little indicator, and nobody can see the indicator the way I have it right now, so let me turn it this way. Okay. Having it on a level, stable surface is important. If you put it on a different surface, it's going to change the calibration. But I put it up here just so you can see. Is this indicator line pointing at 0? Right now you say, no. You know why? At the end of first semester, we have a lab final exam for people in general physics, and we take it uncalibrated, and they're supposed to remember to calibrate it. Whoever used this one last clearly forgot to calibrate. Yes, and that ends up with bad results. You have the wrong mass because you didn't calibrate. So it has a screw back here that you adjust to make it so it will point at the 0. And so I need to go a lot more. Okay, now I'm going to pretend that it's perfectly calibrated now instead of going any further. Then you put the thing on that you want to measure the mass of. Oh, what the heck. Let's actually try to do it right. And I'll measure the mass of one of these bars. We're going to take it on faith. These bars are 500 grams. I'm going to see how good that faith really is. So if I'm going to calibrate it, I'm going to have to be a little more careful. It's very frustrating for me because just like the reason I don't sit on nails is because I tend to be herky-jerky. I let go of this thing and it moves all over the place because, I just call me a lurch. Come on. Okay, that's pretty good now, 0.0. So I put this on. First thing you do is you take the heaviest one and you bring it out until it goes down. Now, this went down to 500. That means that it weighs less than 500. That's my first because it was supposed to weigh 500. Well, halfway. Having mass up, measuring the mass. So then I bring this back to 400, so it's still up. Then I bring this one out until it goes down. And so now I'm at 400 plus 100 is 500. It should have gone down again. So I bring that back to 90, and then I slide this one across and find the point where the indicator points directly at the 0. Wow, this is light by more than a couple grams. That's stop already. Takes patience. You know what I don't have? Yeah, a lot of patience. Okay, so what I have now is 400 plus 90 plus, and it's between 7.0 and 7.1. So I estimate one digit beyond that. How far is it between 7.0 and 7.1? So look at this, I'd say like 7.02, because it's about 2/10 of the way between. And so I have 497.02 grams. So that's the mass of this. It's supposed to have been 800, so it's off by a fair amount. Or 800, 500. So it's off by a fair amount. I'm surprised. So you're going to measure the mass of your cart and put that in that little, where it's circled. Then you notice it's the 4 hex nuts, so 8 washers. Set the cart, so you're staying with 8 washers, and then you're going to add the mass block to add 500 grams. So this is, your cart is supposed to also have a mass of about 500 grams. And then you're adding 500 grams, so your mass is 1,000 grams roughly. So you doubled the mass. That's the theory. And then you're going to do the experiment again. First, you predict what's going to happen to the acceleration. Then you actually do the experiment. So once again, right here, acceleration equals however meters per second squared you get, and then answer the question. The summing up is where you are taking the information you gathered from those, well, you did a total of 3 experiments, one with 4 washers, one with 8 washers, and one doubling the mass with 8 washers. So that's what you did for experiments. Now you're summing up. So here you are simply going to check one of these 3. Not all of them like I did, but check the one that matches what you found with your experiment. Likewise, you're going to check whichever one here matches with your experiment. So how many are you checking in summing up one? Just one. And how are you determining that? By looking at the results. For summing up one, you're looking at the results that you got in part A. And for summing up 2, you're looking at the results you got in part B. Then for step 3, you're filling in these 2 blanks, which you get from looking at your answers for summing up 1 and 2. So you take what you put here between acceleration and force, and so that's going to go right there. And then here, what you put between acceleration and mass goes here. Oh, actually, and blank proportional to the mass of the object. Oh, yeah, the words you're going to put for each one of these is either directly or indirectly. For each one of those, it's just going to be one of those two words. What does directly mean? Directly proportional, I should say. If my weight is directly proportional to my age, what does that mean?
You weigh a certain amount at a certain age. As your age goes up, your weight goes up.
Okay, as my age goes up, as my age goes up, my weight goes up the same amount each year. Direct proportionality. What if my weight was inversely proportional to my age? As my age goes up, my weight would drop. Right, so that's what you're looking at here. Directly as one goes up, the other goes up. Indirectly as one goes up, the other goes down. Both of these, it's acceleration compared to first force and second mass. So acceleration is directly or indirectly proportional to force, and acceleration is directly or indirectly proportional to mass. That's what you're filling in. Then based on your results from this statement, you're going to choose which of these equations matches that statement. If it's proportional, it's on top. If it's inversely proportional, it's on bottom. And then the final thing is, it says, let's suppose that this here is the position versus time graph for 4 washers. So 4 washers is B. And it says, if you doubled it to 8 washers, which line would the graph look like? Would it look like A, B, or C? And so you're going to answer, it will look like, I'll put D because it's not one of the options. Because, notice the explain, you have to have the reason why it would look like your choice. So for this lab, now we had one here that I wrote upload. I want you to once again upload here the graph you make and upload the graph you make here. So once again, you'll have 3 graphs that you upload. This way, when Alex is grading, he can look at your graphs and make sure, yes, you wrote down the acceleration that goes with your graph. Right. So, any questions before we get started? Now, we will be helping you get things set up, and you'll have questions about the setup, I'm sure, as you get going. But any questions about the lab procedure before you get started? No? Okay, groups of 2, 4 groups.